talk of this session. Now I'm glad to introduce one of my academic brothers, Vitor Matos from the University of Porto, and he's going to talk about a class of conservation laws arising in flow in porous media.
Thanks, Pablo. I would like to thank the organization for the invitation. I will talk about, okay, let me put here a clock. Okay. I will show first some bibliography, and among these papers and theses, I would like to tell you that the ideas of Wanderson Lambert are really important here. Probably you will recognize Johansson, Dale from yesterday, and first one too. And this paper from Júlio Daniel Silva and then Marchesin are also important. What I will introduce you here is a generalization of something that myself and then Marchesin we have do it a few weeks ago. I will show you two kinds of problems. The first one is a two conservation law that arise in porous media, where G is the accumulation, F is the transport. This is the Darcy law. And I will compare it with another that has three conservation laws, where the Darcy law is not any more constant, so he must be here. And we get three conservation laws. The problems are quite similar, so I will solve them together. And I will do it for this kind of functions. Actually, it's a question of taste. We may write this like something A 1 minus S plus BS. And here the meaning of these two functions are more clear, since this is one phase and this is another phase. And here I do the same, but with different A and B. Okay, the answer to these problems depend on a lot of matrices and determinants. I will not bore you with all the computations, but I would like to say that since I'm solving two problems at the same time, I have the same letter meaning two different things. In the problem one, A means this determinant, and in the problem two, it means another thing. And here we have the same, and with the other determinants too. We make an assumption, AB plus A and B do not vanish, except probably in some points or something not so important. Well, the first problem leads to a common eigenvalue problem, since if you look for eigenvalues, you have this matrix, but since the determinant of the G is exactly what we ask to be non-zero, we can solve this as a common eigenvalue problem. In the problem 2, we have a different situation. dg is singular, and so we have a generalized eigenvalue problem. And these two problems lead to just two eigenvalues, or characteristic speeds if you want, and both can be written like this. I remember you that A, B, C are not exactly the same in both problems, but if we apply ABC to the correct problem, both have this form. If we wish, you can transform this in this equation, and we have a nice interpretation for the eigenvalues. If we keep y constant, one of the eigenvalues is the derivative of our function f, and the other eigenvalue is the slope of a chord. For instance, if we have our point here, I'm assuming both omega are negative. So the other eigenvalue is this slope. I call this one lambda s and this one lambda e. Okay, these two eigenvalues can be scaled, thinking that the porosity and the Darcy law are constant, and we have two functions that depend only on the variables s and y in both problems. We need another functions. I show here some of them, and some of them plays an important role. Here, the difference between this rho and beta from problem 1 to problem 2 is just this term that has omega u, but again, here omega s is not exactly the same in both problems because we have there a, b, etc. The eigenvectors, the right eigenvectors are like this, and they have some important behavior. One of them is that one of the eigenvalues is always horizontal. Well, in the problem 2, I will project also the eigenvectors in the plane S, Y. And so, in the plane S, Y, we have one of the eigenvectors horizontal. So the rarefactions will keep y constant. And the other is quite different. But when lambda s minus lambda e are equal, these become horizontal, except if this vanishes. But usually, he don't vanish. So in this curve where lambda s equals lambda e, I'm talking about the scaled eigenvalues, both characteristics curves are tangents. Okay, this is quite usually since this curve is called, I put here the left eigenvalues. I will need them when I show that the Huguenot curve is not locally a curve, actually, but, well, I will not bore you with this. This curve is called the coincidence, and at the coincidence, we have only one eigenvectors, except in singular points. Now, let's take a look about the inflection. The inflection is the place where the gradient of lambda is perpendicular to the eigenvector. Well, in the first case of lambda s, it becomes just the inflection points of the f. So the name comes from here, exactly. And the other is like this. So the inflection locus of lambda e contains the coincidence. So if we have here the coincidence, he belongs to the inflection of lambda E. At this point, we may compute the second derivative of the eigenvalue across this curve, and we find this here. So we may know if here we reach a maximum or a minimum of lambda E computing this function. Well, this could be seen in the picture. Let me show you. At first, the coincidence, it's easy to see. It's the point of tangent C between this straight line and the function f. And here, the second derivative of lambda E depends on the second derivative of f, but it's multiplied by two functions, beta and rho, and also divided by this. So if beta, rho, if this is positive, this picture tells us what it happens. Since if we keep y constant and you take a look what happens close to this point, we see that in both sides lambda s is greater than the lambda here. So it's easy to see that we have in the presence of a minimum. But if this is negative, this picture misleads us, since what it happens that even being here, the y almost constant because you are in the presence of a minimum or a maximum, we can make the picture with constant y, since the tangents. So here, y is a second order function of s, and here the tangents too. So we have a competing two things of the same order. So this picture misleads us because actually let me see, okay, because y actually moves, this point could move so fast that actually we have lower eigenvalues close to that point. The examples I know from porous media, this is positive almost of the time on the coincidence. I never saw this case, so I never saw a misleading picture. Okay, we have another problem. On the projection, if instead of C, the inflection as where the eigenvector and the this gradient are perpendicular in the space, if we take a look on the gradient of the scale eigenvalue and the project eigenvector, if we perform this computation, we get this. And this is not the same as we have here, because this term in beta has an omega and not an f. So the coincidence, the inflection that contains the coincidence also contains the points where beta is 0. And here, the project eigenvector and the gradient of lambda E are not perpendicular. So we cannot realize on the projection that we are in the presence of inflection. This could be also a misleading thing, because if we think, oh, they must be perpendicular. Okay, they are perpendicular in this case. In the coincidence, the gradient are actually perpendicular, and but in beta equal 0, they must not be. We don't know. Well, we will see that this is not actually like this in some cases, particular cases. Well, the first case is when C vanishes. So a lot of other things vanishes, and one of the most important things is that in these functions here, we can put lambda E multiplying something. So the inflection becomes the union of three things: the coincidence, the vanishing lambda E, and another set that is when this vanishes. Well, this vanishes exactly in this case when this is 0, and this is equivalent to ask to f equals 0. So we have the inflection now has three branches. One of them is the coincidence. Another is the curve U that Wanderson called it the, what is exactly the name, Wanderson? No, this one, when F equals S in your case, is exceptional? CS? Okay. Here I call it U. Yesterday we saw another name to it. We can show that this curve is a contact curve. So this curve is the integral curve, and the eigenvalue is constant over there. If you try to compute the case C equals 0, we'll find that is highly degenerate, and probably we must do something to solve the problem. But if you try to use this, we get almost everything 0, and it doesn't work, what I'm doing here. Another case is when A and C are equal. Here, omega A and omega C are equal, so I call it just omega. And occurs something similar to the case A, the case C equals 0, that is something can be factorized here. And now it's lambda E minus 1. This is in red because in the problem 1, this not appears, and in the problem 2, it appears this term here. So the inflection is exactly as in the previous case. The coincidence, the case where lambda E equals 1, that could be written like F equal S, and another curve that is where this vanishes. Again, we can prove that this curve U is a contact curve. Okay, as I showed before, in beta, we can put this term multiplying something, and here we can do that because we have this other term. But it's close to have something multiplying that. So if we try to see what happens with lambda E on the coincidence, in the case, if you try to see what happens with I said correctly. If you try to see what happens to the eigenvalue lambda E close to the coincidence, we have this function now where we have rho and beta like this. So I'm in the case where A equals C. So omega lies here. Let's put it here. Now, what I say is that if I have a function f with something like this, with a positive second derivative, here I can compute to try to know how behaves lambda E. And if we have something close here like this, if this is a maximum of lambda E, and if these functions do not change its sign, here is obviously a minimum. But if some of these functions change its sign, something happens and is different. For instance, let's put the point above lambda E equals 1. So if we found this here, this coincidence here, beta changes sign, at least if this not change also. So here we'll be in the presence of a maximum instead of a minimum. But what is nice here, and is what happens in the cases that I know from the porous media, is that this function also will change its own sign. Because this term is really small. So when this changes the sign, this will change just close to the same point. So actually, if we change only beta, it will occur like this. But almost always rho changes sign too. So this here we have a minimum. And as one said yesterday, if we cross the curve from one side to the other, we have a maximum and a minimum, or a minimum and a maximum. So this happens only if this derivative is really small. If this derivative is too big, it could be different. But this derivative is small if we impose something about the flux function. And if we ask that this function f has a shape, is shaped like an S, so you are always keeping this derivative not so much bigger. But in a general case, you could have two maximums, one following the other. Okay, another important thing is that the projection works well on the contact curve. So that problem that I told you, when beta is equal to 0, usually they project not perpendicular. Well, in the case of A equal C, beta splits into curves, and the other is this here equal to 0. And in this curve, the projections is, again, like probably we wish they are perpendicular also in the projection. And in the cases I know, this function is always of the same sign, so this curve doesn't exist. And actually, the inflection, the projection of the inflection, we have always the perpendicularity between the projection of the eigenvalue, eigenvector, and the gradient of the scaled eigenvalue. Well, actually, this could be easily generalized to the case where C equals alpha A, and it's the same. So now here we have F equal lambda S instead of F equal S or F equals 0. This curve is also a contact curve, and the projection works perfectly. Well, I'm close to the final. So let me show you just that we can write the Huguenot curve as an implicit equation like this, but we can do something better than this because there exists a branch that it's really simple. It's an horizontal line, and we can write an implicit equation just for the other branch. So the other branch is given by this. That allow us to compute some things like I probably will not speak about this. This is related with the paper of Julio Daniel Silva and Dan Martin, where we have waves without an intermediate state, but I will skip it. Well, let me see. Okay, I will tell you just one more thing, that is, if we compute the curved branch for a point on the contact curve, imagine that the contact curve is like this. I don't know, something. If we compute just the curved branch for some point here, the Huguenot curve will be exactly U plus the set where this HG that is a determinant that depends only on Y equals 0. So we may have probably some horizontal lines here. This is the curved part, so if we put the trivial branch of the Huguenot, we'll get something like this. Okay, that's all. This is just a review of everything. Thanks.